you can I can share screen with you. Yeah, you can draw
Okay.
any diagram.
Yeah.
Centripetal, centrifugal. So there are two pair of forces acting on a different object. Yes.
And this is a point moving.
Yeah. So
this is the velocity.
Yes,
right?
That's right.
And this say that this a force between, is this the acceleration or the force?
Well, this is directional force. Yes. Okay.
What is it?
Yeah, I can draw a perfect circle like this. All right. So this, if you have the circle, then use the object. See, circular motion. You first step by step. So first motion is objects following the circle, right?
Yes.
So at any position, at any instant, the velocity, direction of velocity is tangent
to the circle.
Is perpendicular to the so the circle. Yes, that's right. So if I draw this, so that would be the velocity. Can you see?
Yes.
And this velocity will change direction all the time. Next moment, the direction will be different. Do you agree?
That's right. Yeah.
So another issue is this is radius.
Yes.
So the distance from the center. Okay. So this is center. So in order to make this object doing the circular motion, a force must be acting on it. On that object. So this is a force. Can you see?
Oh.
Yeah, I should make sure. This should be perpendicular, right? So this two direction must be perpendicular. So I wait one moment. I do it again. So this direction should be perpendicular to that centripetal direction.
Yes.
So that is why this is in this case. The acceleration, if depend, if this uniform circular motion, and this force is perpendicular to the direction of motion. Can you see? This is a perpendicular. This is a perpendicular, right?
The velocity is perpendicular to the force.
Yes, perpendicularly here. Velocity is a perpendicular force. Yes.
Yeah.
And of course, the force either can be, the different force can acting as a centripetal force. In the case of the solar, it
could be tension or gravity.
It could be gravity, yeah. If, for example, it could be can we so this it could be the Coulomb force. It could be the gravitational force. Can you see?
Yeah.
So this force, this direction, the force is toward the center, right? Toward the center. That is so that is two cases where this is a mass and this is a sun. Can you see? This is a sun. This is and this is a proton, and this electron. Can you see?
Yeah.
Of course, proton is positively charged. And so in this case, the centripetal force in this case is Newton's gravitational force, right? That is m capital M and divided by r squared. And in this case, it's Coulomb force. So so the different force can acting as a centripetal force is E, and because this E as in this case, this hydrogen atom they are the same, so that is E squared.
What is the acceleration direction of the mass?
Acceleration depend. You see, acceleration in general could be any direction. But the circular motion can be right down here. So circular motion is if you study uniform. So we study only study uniform. If in many cases we are only study uniform circular motion, right?
Does that mean the acceleration is zero?
Depend. No, it's not. Circular motion. In this case, and we will say that. Probably I'll give you a general description, okay? So in general, the acceleration could be, I draw acceleration now. In general, acceleration could be this direction, you see? In general, if not uniform, it's circular motion. So in this case, this acceleration can have two components. Put it this way, so this is a general case, okay? And they have one is centripetal direction, can you see? That is that case, that would be, this direction would be a centripetal, can you see?
Yes.
Another is called the tangent direction. Can you see?
Yeah.
So this, if I draw that too many, so they have two components, right? And so this is called a tangential direction, or is a T, all right?
Oh, so it moves in the same direction as the velocity.
No.
For the green one.
No, the one is responsible for the acceleration of change in the velocity. Another is responsible for the change of direction of velocity.
Change of direction of.
Yeah. If I, yeah, that's a good question. Can we just? So I just draw here. So if they have the acceleration. Let's do it separate. Yeah, I just focus on acceleration, right? Okay. Acceleration, I just redraw this direction of acceleration, which is in general is not perpendicular to the velocity in this case. In this case, acceleration have two components. One is a centripetal direction. And another is parallel to the velocity, you see?
Yes.
So if I draw it very correct, if I draw it nicely, so that is how to start the vectors, can you see? Any vector can be have two components. So if this is a total acceleration, let's do it again. So that's if this is a total acceleration, that will be acceleration. It's called the centripetal, and this component is called the tangential direction. You see.
Okay.
However, when we start uniform, so when we start, let's do it again. So when we start uniform circular motion, in this case, the tangential acceleration is always equal to 0. Does that make sense? No?
Yes, because
so this is a special case. This is special case, all right?
Yeah.
So in this case, the direction of acceleration is always perpendicular to the velocity.
Yes.
Yes.
Yeah, and I just wonder why, because the force and the acceleration is both pointing towards the center.
Yes.
Why the object fall into the center in that case?
You see the velocity. So basically, velocity and vector are two vectors. You see.
Yeah.
Velocity, and acceleration. So they are different vectors, all right?
Yes.
So in general, they are not parallel, okay? In the special case, they are parallel. If you start the motion of the free fall, it's parallel, can you see? If the object is falling down, can you see?
Yes.
And in this case, the velocity is parallel to the acceleration.
Yes.
Okay. But in this case, in the uniform acceleration, the velocity is perpendicular to the acceleration, you see?
Yes.
So this, let's do another. So in this case, so I use different color here. So the red color is acceleration.
Yeah.
So in this case, this case, the acceleration is a centripetal direction is perpendicular to the velocity if it is uniform, can you see?
Yes.
If it is not uniform, then we have to consider the change in the velocity amplitude.
Yes.
So this is if you do this is how fast the velocity change in the amplitude. Can you see? That's in the amplitude.
Yeah.
And this is so that is how we that's why in high school physics we always, in many cases, we assume that the circular motion is uniform.
Yeah.
So that is why it's always 90 degrees.
Uh-huh.
Perhaps you will ask why it is perpendicular, because in this case velocity is constant. Can you see? The velocity is a constant. The speed is constant. Can you see? It's not changing. You see.
Mm-hmm.
So, by definition, acceleration is a change of velocity, right? That is the definition of acceleration.
Yeah.
So acceleration change that involves two parts. One is a change in the direction of velocity. Another is a change in the magnitude.
What does magnitude mean?
Magnitude is any vectors. Magnitude is
the magnitude of velocity.
It's just the value of the length. You see, this is velocity, right? So that the length is called the magnitude. Can you see?
Yeah, I get the magnitude. Yeah. I just don't know which magnitude you're referring. The velocity?
Well, in the uniform circular motion, velocity only change direction, not the magnitude.
Yeah.
But in the so that is why whenever we describe the acceleration for the uniform circular motion, we know that the direction of acceleration is toward the center.
Yes. So why wouldn't it fall into the center though? Is there any other force acting on the body? No,
you see, have you studied this formula? Have you studied this formula? Acceleration, centripetal acceleration, the magnitude is equal to v squared divided by r. Have you studied this formula before?
Yes.
Yes. Do you know why? That is how this in this case I can show you. So if you know how to derive, do you know how to derive this formula? Yes. Yeah, you do? Yeah. Derive? Or derive? No. How to obtain this formula? How to prove this formula? Yes, let's show you. So let's show you how to do that. So if the velocity, if they just prove why this formula is that, okay. Mm-hmm. So if this is so this is velocity at that moment, all right, and after a while, the object will move to this different position after delta t. Yes. Can we draw this after delta t? It will move to that direction. Can you see? Change it. All right. So in this case, velocity will change the direction. Can you see? Velocity will go that direction. Yeah. But the length or the magnitude is the same. Yeah. When we talk about magnitude, we are talking about the length of this arrow. Can you see? Uh-huh. So how can we prove that? Now what we can do? We can shift this initial velocity. This initial velocity, right? We can shift this vector to here. Can we? Yeah. Okay. This is initial velocity. That is after delta t. Yes. So in this way, then we will work out another triangle here. So this one, all right? If I use a different color, so this would be the difference. Can you see? One moment. So that would be the change in the velocity. Have you studied the vector difference? Yes. Mm-hmm. So that is so basically this is initial velocity, right? Yeah. And this is the final velocity. So this is the final velocity. So this would be the change in the velocity. Because the change in velocity can be written as the final velocity take
Yes.
the initial velocity.
Mm-hmm.
Do you agree?
Yeah.
So in the meantime, we can use R to represent this distance from the center. So this is the center. Can we call this O? Is the center, right? So this is a P. This is position P. This is position Q. Okay. So you can imagine that the object has moved during the delta t from here to here. You see.
Mm-hmm.
Now, if the angle is small enough, so this distance, can I draw another distance? So this distance will be very close to that arc. You see, if the angle is big, it's not. There's a difference. If the angle is very small, this length and this arc will be the same. You agree?
Yes. Yeah.
So therefore, what can we do? So we can show that these two triangles are similar. You see, this angle is also the theta.
Yeah.
You can do that. You can use some geometry to prove these angles are the same. So in other words, these two triangles are similar triangle.
Yes.
So what we can do is that, so if we use so this distance is a proportion to the velocity multiplied the time. You see, so it's so PQ. One moment. So PQ is very approximately equal to the V times delta t. Do you agree?
Yes.
And the V times delta t, and also this because these two triangles are similar, so therefore R over is PQ, yes, so PQ over R must be equal to the change in the velocity, delta V, can you see?
Yes.
Delta V over V. Can you see that?
Yeah.
Okay, if we just substitute, if we solve these two equations, we got V delta T over R equal to delta V over V. Can you see?
Yeah.
Then by solving this one, we can work out the acceleration. Delta V delta T will equal to V squared R. So delta V delta T, what is delta V delta T? That is a change in the velocity, right?
Mm-hmm.
The change in the direction of velocity. So therefore, this this is exactly equal to our acceleration toward the center. You see?
Oh.
Can you see that?
Yeah.
So this exactly, so because we have used acceleration here, by definition, is a change in the velocity over R at delta t, all right? But this approximation, of course, to be exact, you have to use the calculus. You have net delta t equal to 0. Do you use this sign? Do you use this net in calculus? We use this notation. You see?
Yes.
That would be the first derivative, dv dt. Can you see? So this is a proof of this formula for uniform circular motion. You see that?
Yes.
Can you understand why the formula is, why the acceleration is also another thing? So from this diagram, you can see as theta getting to 0, so this arrow, this change, so this became parallel to the, so this arrow were parallel to this direction. Can you see? If I draw another thing, so this is the direction of the acceleration. Can you see?
Yeah.
You can imagine that if theta is getting small, so this arrow will be parallel to this one. Can you follow me?
Yeah.
Yeah, any question?
Still getting my head around this.
You see, you have this. I don't know if it's that convincing. So if you have velocity, vector sum, if you have two vectors, so this is very useful. If you have two vector, for example, if you have the one vector, another vector is another. I use different color this time. So another vector is this. One moment. There's another vector. Okay. Now, how can we find the difference between these two? When you start math, how do we find the difference between A and B? What is A? How to use a graphical method to represent A? Take A minus B.
You draw the reverse direction of B and
Can you draw from your side?
Yeah. This is minus B. Oh.
You want to go backward, right? But
Yeah.
after you have started that, yeah, that's negative B, right? This negative B. And you got, but if ultimately, so use the sum formula, right?
Yes.
The sum will be the diagonal. Can you see that? Yeah. And this one is also equal to this direction. Can you see?
Yes.
Is also equal to that. So when you know how to derive this formula for vector difference, then we just found this. We just use this arrow. Can you see? So this one is so this is what I'm looking for. This vector, that vector represents difference. So that is exactly what we used here. Can you see? So this is initial velocity. Can you see? This is final velocity. So that's why can you see? We use a vector formula. You see. So if you use formula, so you should be able to understand the change in the velocity can be graphically displayed by this arrow.
Yeah, I get all of that. I just don't understand why it doesn't fall into the center still.
Oh, you can see this is another thing is this is actually because t have no direction, time has no direction. Can you see? Yes. You can start from here. You can start from here. Can you see? So acceleration must be parallel to the delta v. Can you see that? Yeah. If I draw the diagram, so therefore, if I use this if this acceleration, so acceleration or different lengths, all right? Can you see? Yeah. But the mass in this direction. Can you see? If you move here, well, it's slightly different because it's not toward the center. That is because this theta is not small enough. You see, if theta is small enough, you will see that the delta v direction will be toward or central P2, toward the center. Okay. Well, another thing is that you see, another thing is if you consider the object is moving, right? If the object is moving towards let's say this is these objects moving upward, all right? You can imagine some like if you launch a rocket, all right? The rocket vertically move upward, okay? Now, if there's wind towards direction, the wind, okay, if during the launch of the rocket, the wind will come. So what would be the direction of this rocket?
Tilted to the right.
To the right, can you see? They change direction, okay? The reason they change direction because that the force is in this case perpendicular. Can you see?
Oh, I think
can you see that?
Yeah.
That makes sense. It's just sometimes you have to use the common sense to so therefore acceleration is perpendicular. Can you see?
So in this case, the object is moving upwards.
Yeah,
but
moving upward.
The centripetal force is tilted it towards.
And this is, by the way, this would be the part of circle. Can you see? It's part of circle. Imagine it's just use common sense, right?
That makes more sense.
Yeah.
I've been struggling with this for like a year.
For a while.
Yeah.
Yeah.
Thank
So
you.
you see, so Newton's law is very useful. Can you see? Newton's law can be applied in both directions. Can you see? So Newton's law says because our centripetal force, therefore they have centripetal force. Can you see? Centripetal force must be just multiply the mass, multiply this acceleration. Can you see?
Yeah.
Okay. So centripetal force, another issue is that the force acting on the object during the circular motion is called a centripetal force, right?
Yeah.
And so if I draw this, force is toward the center, right? So this force is called the centripetal force. Okay. Okay. This is C. So centripetal is a centripetal. Okay. Petal force. Not P, but F. F-O-R-C. Another force is called a centrifugal. Have you heard of centrifugal?
Not at all.
Yeah, central. I just put two centrifugal. Fugal force. So these forces are action and reaction according to Newton's third law. So if the object's doing the is doing the circular motion, right?
Yes.
And you know that there must be the force perpendicular to that object, right? So this force toward the center of the circle, this is center. Can you see?
Yes.
And of course, in the center, we know that this must. So in the meantime, in the case of the solar system, you know that according to Newton's law, there be the force also acting on that center object. Can you see?
Yes. Yes.
In this case, is the sun, right?
Oh.
And these two forces are just a pair of action and reaction. Can you see?
Yeah.
So this is centripetal force. You see, they all C, okay, centripetal force, and this will be the centrifugal force, which is opposite, but but they are the same in aptitude.
Oh.
So in other words, if the object is moving about the object, so the moving object also exerted the force on the object at the center.
Oh, yeah.
That makes sense.
Not moving.
Yeah. However, so that force is opposite. If you draw here, the centrifugal force in this case is as if they are just toward outside. Can you see, away from center? So this is the center. Can you see, this is the center? This is the center. So centripetal force is toward the center. Can you see? The centripetal force is toward the center. Okay. But the centrifugal force is away from center.
Yes.
But this centrifugal force is acting on the object which holds that moving object.
Oh, I can understand it with like a string where
string. Yeah, that's right. Yeah.
Yeah, the tension on the smaller objects.
Yeah, and we can talk about different scenarios. So if you have your string, yeah, that's right. If you use a string, okay, or you can consider this is an object. This is a table. I often draw different scenarios. So if I just consider this is a table, right? If you draw the hole here, and you put it through a string, and you put the weight here. Okay?
Yes.
This is mass m, and then the object is connected with this another mass. This is mass 2. Is mass 1. Can you see? So you can make this object doing the circular motion on this table. Now this time, they still need to, let's draw it again. Just draw the circle instead. Can you see that?
Yeah.
So they are doing circular motion. So in this case, they must provide a centripetal force towards the center. Can you see? And in this case, the centripetal force, is the tension. Does it make sense?
Yes.
So if you draw to isolate this object, and the tension will be towards the center. Can you see?
Mm-hmm.
That tension will acting as a centripetal force.
Yes.
Of course, in this case you have considered other force. One is gravity. You see?
Yeah.
Gravity is. So gravity is downward, okay? And also another force which is normal directional force. Can you see?
Yeah.
This is gravity, right? mg. So this is tension. Tension acting as the centripetal force.
Yes. Does it mean the centrifugal force is also acting on the opposite direction?
No, you don't. That force is acting on M2.
Yeah.
Centrifugal force is acting on M2.
Does it mean they cancel out because they have the same magnitude?
Oh, they're balanced. Yes, they're balanced. They are equal in magnitude, but opposite in direction. So as a whole, there's the total force internally is zero. Can you see? That's Newton's idea. Can you see? If you're talking about, you cannot talk about the force, a single force. Can you see? If you have two objects, right? Object one, object two. Now, if they attract to each other, okay. If just like gravity.
Yeah.
So then you should consider two force. Okay.
Yes.
Yes, you are right. If you put the two forces together, the total force is zero. But this force is not zero on each object.
Yes, that makes sense.
That makes sense.
Uh-huh. But like in the case of tension, I can like.
Yeah, the tension can also provide as force acting as a centripetal force. Okay.
Like I can imagine the tension forces cancel out on the string, but I can't imagine the gravitational force cancel out on two bodies.
Oh, so because you see, according to Newton's law, the formula just tells the amplitude. See, can we just return to the Newton's gravity, right? So this is Newton's formula. This is Newton's formula for gravity, gravitational force, and that is r is distance between the two objects. Can you see that?
Mm-hmm.
Now, when we this formula can describe either forces. Can you see? So this force. Can you see? This is another force. If you use a vector, sometimes I use a subscript. This is a force of two acting on object two, originate from come from the object one. Can you see?
Mm-hmm.
So that's how I use this subscript to describe this force. So from this diagram, you know that these two forces are opposite in direction. Can you see?
Yes.
But they are in aptitude according to Newton's third law.
Yes.
The reason we didn't consider this force, which is a centrifugal force, because normally if m is very large than this another force, the object is not moving. It's not doing circular motion.
Yes.
Maybe when we encounter the question, we can spend more time to discuss this issue.
Yeah.
So Newton has three laws. Okay. Although we use the second law all the time, but don't forget that he had the third law. The third law said any force must be show up as a pair. That is why force is also called interaction. Yeah. Okay.
Okay.
So for example, if you go to if you consider a spring, okay. So you have the spring. So this is normally we consider it called the massless spring, right? So this is initial position. This is a equilibrium position. if you just extended that object by that much, so therefore the displacement of this spring is x, you see? So by common sense, you know that there's a force to pull the object backward, you see?
Yeah.
If there's no external force, if there's no other external force, and this object will move, right? But in the meantime, you don't forget this object is also have exerted force on the spring.
Yes, I think the common objects are easier to understand, but not gravity, because the string can stretch and can compress, but gravity can only attract but not repel. So I just don't understand how can
good idea, because we don't need to repulse, you see. Because Newton, don't just remember Newton's is attraction. They can only attract, okay? They cannot repulse. If they repulse, they cannot do circular motion. For example, if you put, that's a good question though. If you put a pair of a positive charge, right? And they cannot circulate, they can never circulate to each other. Because the force is, the direction of force is repulsive, you see.
Yes.
Okay. So that's why Newton came out this idea that the gravitation must be attraction in the first place. Okay.
I'll have a think about it after this lesson.
Yes, okay, doesn't matter. Shall we move to that any other subject we were studying?
Yes, please.
Let's just say, last time we spent 1 hour on the Bohr model. So Bohr model is part of this so-called natural world, right? Maybe we can use some of the pictures I prepared before. And I think let's go to share the screen. That's right. I just use this one. We almost finished your topic you give me, right?
Yes.
And now probably we can go to some more detail. As you can see, I already put some formula inside. We are moving to the natural world now. Can you see?
Yeah.
So last time we discussed the Bohr model. So which the Bohr model. And by the way, the electron in the hydrogen atom is also doing circular motion. And also that centripetal force is acting by the Coulomb force, right?
Yeah.
It's also attraction. Okay. So that is why when people first encounter that atomic model, nuclear model, then immediately people thought that perhaps we can use the solar system. We can describe the electron in the way we describe each planet in the solar system. Okay. Of course, Bohr model has added a different condition so that only a few orbitals are stable, called the stationary orbit. Okay. And I think natural world is just mainly about the solar system, involved of course, Newton's gravitational law. Can you see?
I can't see your document.
Can I can
only see
sorry, I should share this one. Thank you. Let me know. I need to share the screen. Can you see my? Yeah, you can see now. Okay, so we are since last time we are talking about natural world. Okay, atom is a small world, small natural world. A larger, a lot bigger object than the Earth is the solar system. So you need to know some of the basic idea. For example, the phrases or different name of the moon. Okay, I remember you asked me, do I have to memorize? You don't have to. Just for example, you need to know what is a new moon, what is a full moon. That's all.
Oh, okay.
You see that? And the new moon is dark, and full moon is a circle, the bright circle. Okay. Anything in between, you don't have to memorize that. They will tell you, or they will even provide the pictures. Okay.
Oh.
Okay.
Then what are they testing on then?
Well, we will see.
Yeah.
That's why I suggest that probably from next time we will use a past paper now. Do you agree?
Yeah, we can start next lesson.
Yes. So today we probably just also eclipse. You know the eclipse?
No.
They have the solar eclipse or as moon eclipse. Have you seen any eclipse before? Suddenly, the day became night.
Yeah, I know they are.
Do you know what happened? Do you know what happened? That is because the moon moved in between. You see, if I draw the diagram for you.
Then what happened when sun eclipse?
Yeah, there's a solar eclipse and the moon eclipse. So I will just stop sharing this one. I can draw these two scenarios. So basically, you need to know that there's a sun. The sun is can we draw the sun over here? You see this sun, and in the solar system, the sun is a star, so the sun can generate light and radiation. Yes. Other planets like Earth have no, is very cold. Okay, the surface is very cold. And so the Earth, you have to draw the Earth. You have to draw the Earth. Earth is orbit about the sun. You see. Yes. Maybe I use this coloring. So the Earth is moving about the sun. Should be much smaller, right? Yeah. And in the meantime, the moon is orbit about the Earth, right? So this could be this scenario. If that is the case, because you can see this is called a solar eclipse. Yes. If I draw the night, so in this case, the sunlight will be blocked. Can you see? This is exaggerating. So the sunlight will be this sun can go through that. Okay. Yeah. And this of course this sun is much smaller than this drawing. Okay. Yeah. So anything behind the moon, in this case, perhaps will make it more real. So basically, the moon, so this moon only part is bright. Can you see? How can I show that? So so that is the moon. In this case, then we just see the black ball in the sky. Can you see? Yes. Okay, so that one, so this part became dark. Can you see? That is the shadow of the moon. Do you agree? Yes. So you can imagine that if you happen to be in that area, so that is can we draw the map here? So if this is a map, can you see? If this island, this map, can you see? If you live in this dark shadow area during the day, and all of a sudden you couldn't see, it's become dark. Oh, but isn't the moon like really small? Why would the sun be fully blocked? Well, because yes, this is exaggerated. So it is exaggerated. So actually, the size of the moon is smaller. So therefore, the shadow, the area of shadow is much smaller. So only a few cities can watch that that dark the shadow of the moon. All right. Yeah. So that is a solar eclipse, right? And I think we have a solar eclipse very, which year? I think it's 2008. 2008. Do you have any memory? 2008? No, probably too young. Okay, yeah. I was 4 years old. Oh, well, you forgot because yes, I remember. Isn't really rare. Oh yes, very strange. All of a sudden, so you just imagine all of a sudden, and the sun disappeared. Sun, not suddenly, gradually. That is if you look at the sun direction, the sun will, of course, without the moon, the sun is so bright we can hardly see the sun. All right. But when you actually, if I draw this diagram, so this is the sun here. So normally we say sun is like this circle, right? And when the moon is moving, the moon is moving. So gradually, so you will see part of the sun is blocked. So that is a part of things like this. Of course, the age is not so clear. So this is let's just draw this. So the age is not so clear. Can you see?
Oh.
Okay, so you will see the sun is broken like this. Okay, and yeah, that is at the beginning, and if the at the next moment, at exactly when sun is blocked, you will see that the moon will be like this. I just drew this picture.
Oh, it's like a ring.
Oh, yeah. You will see. Can we draw the word? Because the sun is in the distance. Okay, so there's actually they can you see? Can you see my drawing? Can you see?
Yes, yes.
You can. It is of course some region you can only see partly blocked. Can you see?
Oh.
In the perfect region, you will see it's completely blocked. Can you see?
Yeah.
You can that is a very close to the. Can you see that is a solar eclipse? do you like my drawing? You can use YouTube to see what the solar eclipse looks like, right? So this is solar eclipse, and so therefore, if you another thing is I saw a relevant question in the PAT test that they just say, you see, you can see this is you can use the eye to describe the brightness. All right, that is intensity. Okay, intensity, intensity, and also they have different names. They call the luminosity. Luminosity.
Yeah.
Luminosity. Osity, how to say osity. So it's just the same thing. So we just use the intensity. Intensity is a proper physical name, right? A property. If you draw the diagram, I noticed there is a question. They say, well, when in the solar eclipse happen, you can argue that the intensity of the sun is changing. Can you see? So the intensity of sun is very bright. Okay. And then when the solar eclipse happens, it changes brightness. Can you see?
Yes.
And then go up. Can you see? So this is time dependent intensity of the sun during the solar eclipse. Another issue is moon is what lunar. It's called lunar. Lunar means moon. If the lunar eclipse, so that is have you seen the? I think recently, just have you seen that pink moon? Pink, the moon changes the color.
Yeah, it's so yellowish.
Yellowish. Do you know why?
No.
That is the shadow of Earth.
Oh.
Can you see? So that's can I draw this here? So we can still draw the sun over here. Can you see? The sun over here. The Earth is in between this time. We just draw Earth over here. Can you see?
Yes, and the moon's on.
And moon is on the other side. So you can imagine, depending on the position of the moon, where is the moon? So in this case, you cannot block the sun rays. Can you see? But if the moon is behind the Earth, so you will see these. Can you see it's partially blocked? Can you see? Let's just consume. Let's just consider it partially blocked, okay, not completely blocked. So you can see that the sun ray cannot reach the moon completely. Okay, the sun ray can reach. Can you see that can reach the part, and that can reach part. But some ray will be blocked. Can you see? So in other words, this time the moon will changes the color. The reason it changes color because so that I can see that is a shadow. Can you see?
Yes.
So can you see, or even darker, even you can go to even getting darker, can you see? Okay.
But wouldn't that become one of the faces?
That is another issue. So this is why they have different phrases. That is because, can we draw the circle here? So the circle is I can draw this simple circle. can you see? You can imagine the Earth, the Moon is orbit about the Sun. Can you see? Okay. Now, in the depending on the different position, we can argue that the Moon looks different. Can we just draw the Moon? So the Moon could be here. Okay. The Moon could be here, and the Moon could be here. And depending on the day of the year, right? The Moon every month they orbit about the Sun roughly. One turn. So therefore, you will see in 1 month you will see the Moon change their faces. Okay. And just draw another 2. Then we can actually Google some for you. So in this case, you can argue that if we look down, if you look up, look at the Moon from the Earth, and this one, these 2 is partly brighter. Can you see that?
Yeah.
So this side is dark. Can you see? And so does this one. Can you see? Yes. So 1 month, this happened twice. Can you see? And but in this case, it is a full moon. Can you see? There's no shadow.
Oh.
There's no shadow. Can you see? That's right. There's sometimes if you look at sky in Australia, it's very clear. You can, after the sunset, you can watch the sky. Okay, that will teach you a lot of this natural phenomena. It's very bright, and so in this case, we will see only part of. See, it's very strange. So that is downward. Can you see?
Yes.
Have you seen this type of the moon after sunset? Can you see after sunset? Yes, this sounds right.
I always thought the moon is like covered by Earth, so that it has like a. Not
always, and depending on where you are, can you see the observer? We just assume the observer is here. Can you see? So if the observer is here, they will see the moon like this. Can you see? Yeah. But if you can imagine that if you just move downward, okay, if the move was downward, that's a good question. If the movement was downwards, if the moon over here, can you see that if you move to over here, you will see that the moon will get completely dark.
Yes.
Because this was blocked by the sun. You see. So that's completely blocked. You see. So this is probably partly blocked. You see. So that is the sun from the new moon to the full moon. They will have this change. Maybe we can return to their diagram, the printed diagram, that give you a summary. So this is where is my here? Can you see that? If I enlarge this picture, we can enlarge this picture. Can you see my picture?
No, you didn't share.
Oh, I didn't share. I should share this one. I stopped that one. 1 moment. I should return to the meeting. Okay, I share this time. I share the screen. That's probably the right way to go. Yeah, can you see my screen? You can see my screen now. So look at this picture. Can you see that is a picture of different faces? Can you see? So you started from new moon, which is completely dark, right? Which is completely blocked by the Earth.
Yes.
Okay. And then you can see this. You can see this full moon. You see, and yeah.
Is the full moon like just beside new moon?
No, they will change gradually. So this you can consider this shadow is the Earth. Okay. Oh, it's not necessarily Earth, but it's because the moon is a sphere.
Yes.
The moon is a sphere. Yeah.
Okay.
And I think in this context, you don't spend too much time to get worry about these different phases. The idea is that since Isaac Newton, we know that the gravity is a force which exist between different objects in sky, including on the Earth. So therefore, you should concentrate on, if I am on the moon rather than the Earth, what would be the gravitational acceleration? Have you considered this question?
Yes, I think we have that on our exams.
Have done exam. Do you think the gravitational acceleration increase or decrease?
Decreased.
Decrease. Why?
Yeah, because it has lower mass.
The mass is the issue. So basically, if that is something you need to know. Let's just draw this picture for you. So we don't have to pay too much attention for these names, okay, of the different phases. Basically, they are asking you. So for example, we will use this for any object is spherical. Can you see? Can we just consider any object? This time we just consider object like this, right? And it could be the Earth, could be the Mars. Can you see? Could be any planet, or it could include the sun. So if we know the R, the capital R is the radius, okay? Now at this surface, the gravitational acceleration at the surface can be written as this formula. That is a G multiply the mass of this object, of this planet, could be the moon, and divided by the radius square.
Yes.
Do you know how did we derive this formula?
No.
Yeah, we from Newton's law. Can you see? There's Newton's gravitational law. So the Newton's gravitational law, say that the force between the object, can you see this is a small tiny object M, can you see?
Yeah.
And between the two objects can be written as G, the constant, multiply the product of two mass and divided by the distance square. Now, this distance is between the mass center. Okay, so this is called the mass center. Okay.
Yeah.
So that is why the force between this planet and this tiny object is equivalent to this force between the two point mass. You see, with distance of r. So you can still apply Newton's gravitational law.
Yes.
Right. On the other hand, according to Newton's second law, Newton's second law, they say the force is also equal to the acceleration multiplied the mass. Can you see?
Yes.
Or they use A, in general use A. Okay. So what we can do? So this is equation 1. This is equation 2. So we can rewrite. We can first rewrite equation 1. So rewrite equation 1. We just put the M, the object that we're interested in, and put the GM inside. Can you see? GM squared. Can you see that? So we can introduce something called G. Can you see?
Yes.
We can multiply the M multiply G. So what is G? So that is the formula. G is equal to G multiply the mass divided by R. Can you see? R squared. So if you compare these two equations, you know that in this case, the acceleration in this case is equal to G. Can you see? Equal to GM multiply R squared.
Yeah.
So be careful. This formula is true at the surface. Okay, that is near the surface. Near the surface. That's formula. If you use the radius of the planet, that's the near the surface. That's why in this case for the Earth it's very close to 9.8. Do you know this number?
Yes.
Yeah, that is for the Earth. For the Earth, okay. This time is for the Earth.
Mhm.
You are right, because the moon, the mass of the moon is very is almost a quarter. You see, so it's
Yes.
about the quarter of the mass of the Earth. So that's why the gravitational acceleration is also very close to the quarter.
Yeah.
Okay. However, if you are dealing with a satellite, can you see if this is a satellite, okay? Satellite. If I use a satellite, then you have to use this distance, can you see?
Yes.
So
Oh,
be,
we
so
did
be
that.
careful, yeah.
Yeah.
Then you have the height, this is the height, is the h, right? From the ground. So
You
in
add
that case, the g must be equal to g multiply m, and the distance will be the radius of the Earth multiply added that h. Can you see?
Yeah.
Can you see that?
Uh-huh.
You have to be careful when you're dealing with a satellite, which is above the surface. Then you cannot assume this is a constant anymore.
Yeah.
Maybe this at this place the constant, the gravitation when you're on the satellite is very close to this the gravitation acceleration on the moon now. You see?
Yes.
Yeah. Because another thing you need to use a graph. Another way I will show you when we solve the problem. If you use a graph, that will help you to understand that. Okay. So gravitation, if you draw this the graph, and you know that the gravitational acceleration is a decrease like this. Can you see?
Yes.
So therefore, you can learn more. You know that far from the center, the gravitational acceleration will decrease.
Yes.
If you use infinity, if you move in a very empty space in the universe, so you wouldn't fear any gravity from sun or from the moon at all, right? Yeah. Or from Earth at all. So in that, so you can argue that if the R approach to infinity, then the gravitational will also approach to infinity. You see?
Zero.
Zero. Yeah. Yes. So that sometimes we will use this way of thinking to solve the problem. Okay, we can probably pick up the older paper next time now. All right.
Okay.
Because
do the topic of, I don't know what's that called. Like, why is the moon always like have one side facing the Earth? Is it because of it's locked or something? It's called 潮汐锁定. Do we need to know that?
Well, you have the why the face, that is because it's good. There's something to do with the spin of the Earth, of the moon. Okay, you see the reason we can only say part of that is because when the orbit about the Earth, right? When the orbit about the Earth, they also the spin. So they have the spin, but you have considered it's also spin. Can you see?
Yes.
So that's why we always say on the part one face, not on the other side here. We can discuss that exactly when we actually solve the problem. All right.
Okay. Yeah.
And because you see, our Earth orbit about the sun. Do you agree?
Yes.
That about the sun. But in the meantime, our Earth also is rotating. Can you see?
Yes.
So that is so don't forget about this called self-rotation. It's called a spin. It's called a spin.
Yeah.
And actually, electron also spin. Electron also spin. Okay. So we can continue next time. Yeah. Okay.
Thank you.
Okay. See you next time. Goodbye.